what are the various fabrication steps that are required to fabricate a single MOSFET transistor? What are the steps involved? Remember, in digital circuits, we are talking about huge number of transistors. It's going from billion to 500 billion transistor on a chip. It's a huge number. Okay, 10 to power 9 and going up to 10 to power 11, 12 of that order, that number of transistors. But the steps in that particular, the only thing that is happening is the transistor size is being scaled down. So there are different methods in which the overall performance of your circuits is continuously getting improved. So that can be in terms of its architecture, like you would be studying about the RISC or CIS type of architecture, or one Niemann architecture, or Howard architecture, so on and so forth. Then it is in terms of your design aspect, like how do you make better design of one particular technology. So basically, if your transistor size is fixed, right? Transistor size is not scaled down and it is fixed. Say at a technology node 0.18. Remember, at the very beginning, it all started with 10 micron. Okay, 10 micrometer. What? How much is 10 micrometer? Anybody? How much is 10 micrometer? Hello? How much is 10 micro?
Sir, 10 to the power minus 5 meter.
Micron is minus 6, right?
Yes, sir.
Milli is 10 minus 3. Micro is 10 to power minus 6. Nano is 10 to power minus 9. Pico is 10 to power minus 12. And femto is 10 to power minus 15. So 10 is 10 into 10 to power minus 6 meters. So that was the dimension of your channel length or gate length when it all started. Initially, it all started with a simple MOSFET. Slowly, we graduated into CMOS. Okay, so way back in the 1970s or 1971, the microprocessor that was designed and fabricated and was available, that was of such large dimension. That is the reason why you are you were having such bulky devices, and all discrete devices used to occupy so much space. Now,
Sir,
like in the smartphones and all. Hello.
sir, are you supposed to be sharing your screen because we can't see your screen?
I'm sharing the screen also. Yeah.
Sir, no, it's not shared.
You can't see.
No, sir.
No, sir.
Can you see it now?
Yes, sir.
Yes, sir.
Okay. So as time progressed, using this constant field scaling and constant voltage scaling. I think I'm going to have another class tomorrow. So the lab session which you are supposed to have would be kind of, I will just talk to Mansa before the exam so that we are able to do some more things before we go into the exam part of it. But let me not break the continuity. So since 1970s, the whole idea has been to continuously scale down the transistor. So though there are different ways to improve upon your chips in terms of its performance matrix. Okay, but the Moore's law happens to be the guiding principle. Why? Because if you squeeze down the transistor, the improvement in the performance parameter is maximum. Okay, you are able to have almost double the performance with respect to previous generation. So that has been the criteria to continuously which has continuously driven us to pursue this approach. Though in terms of digital IC design, there has been continuously improvement. In terms of analog IC design, there has been continuous improvement, and also in looking into the future. Similarly, at the architecture level, similarly at all levels. So right from the very beginning, the idea has been to continuously improve the performance of your chips. So that can be by making things more better in the sense that better in terms of speed, better in terms of uh, uh, leakage, better in terms of power consumption, better in terms of capacity, to have bigger memories or bigger or um, more modules within that chip, to have system on chip, or the whole die on chip, something having more and more of these so-called discrete digital blocks encaptured into the same chip area. So that is been the goal. But as we said, the building block has been, for all the cases, the transistor. And most of the times, whenever we are talking about transistor, we are actually referring to the MOSFET transistor. Okay, so one needs to fabricate these types of transistors. So how do you do that? So fabricate is basically manufacturing of this chip. So what are the basic steps that are followed for a single MOSFET transistor? That should be known, because as you go further, these steps may become complicated, because you may have smaller chips and you may have different layers of interconnects. So like if you have, what are these interconnects? Interconnects are basically wiring different transistors to make it into a meaningful circuits. Like if you talk about the gates, there you are having connection to the VDD, connection to the ground, connection to the input, connection to the output. Okay, and your PMOS is connected to your NMOS transistor. PMOS is connected to the NMOS current. So all these interconnects are required to have the input, to have the output, to have your uh, drain of PMOS going to the voltage source, and the source of your NMOS going to the ground level. And then, like in a simple NOT gate, which is like your CMOS and NOT is the same, right? CMOS and NOT is the same. So this CMOS requires two transistors, one PMOS and one NMOS, and that needs to be fabricated. So let's talk about because this is just the introductory part. We shall just talk at the very basic levels, and you can see such things at an advanced level as time progresses. So this needs to be fabricated in a manufacturing plant, which is called as fabs. It's a kind of a clean room environment where you see all those people wearing bunny suits, so that there is no external pollution that is happening. So no external pollution basically means that the air quality inside is such that the number of dust particles within that so-called clean room, which are defined by the number of dust particles per cubic meter, cubic centimeter. So depending upon the dust particles that are available, you have these clean room defined into different categories. And most of the fabrication happens in such type of clean room. So they create a clean room. They kind of vacuum the whole area where your fabrication of the chips is happening. And depending upon the sensitivity, it is done at different levels. You have class 10, class 100, class 1000 clean room, where you are having all these fabrication. And it involves various steps, and we are going to be talking about those steps.
Sir, I think your screen is frozen on the same slide.
No, I have not changed. I have not changed. I will also give you, you can also, yeah. So let's just talk about the various steps for a single MOSFET transistor. In that, you create a N-well region and channel stop region. So what is N-well region? N-well region is basically if you have a silicon substrate which is intrinsic in nature. What does intrinsic basically means? That it has density of 10 to the power of the order of 10 to the power 10 per centimeter cube. So that is an intrinsic semiconductor, silicon semiconductor, in which you form a N weld. So you do ion implantation and make a N weld into the substrate. And then you have probably at the defined areas channel stop regions. So you note down, this is the first step that happens in the in fabricating your transistor. Simple, very simple transistors, MOSFET transistors. So what you do is you make N-well out of the substrate and you create the channel stop regions. The second step is to have the insulator region. To have the insulator region. So what is the insulator region? It is the silicon dioxide. Remember, MOSFET is metal oxide semiconductor. So oxide basically is your silicon dioxide. That silicon dioxide is a dielectric. So that is why we call metal. Metal is basically polysilicon most of the times. But also you have the real metals. So polysilicon is a silicon which is closer to the properties of metals. So you already know the difference between metal, semiconductor, and insulator. So it's got to do with the band gap. So as you so between your semiconductor and metal, the band gap basically reduce and goes to extent that it overlaps so that you have free electron movement. So polysilicon is a material which is having the properties as same as that of a metal. Okay, so you grow the field oxide, which is your insulator, right? So you have, so that is just above the substrate. Then you deposit and pattern the polysilicon layer. This is what this polysilicon layer acts as your metal layer. Please note down these steps. Deposit and pattern the polysilicon layer. Deposit and pattern. So pattern is basically giving uh, the baseline, to the device architecture by continuously doing three things: deposition, then you expose the region that you want to either get dissolved or to retain by using different types of photoresist. They can be positive photoresist. Expose the region using either ultraviolet and nowadays into your extreme UV light. So you form different types of patterns. So you deposit and pattern the polysilicon layer. Please note down, and I think as time progresses, you will understand things better. Once you have this patterning of the polysilicon, you go to the next step, which is implantation of source and drain region. So there is a ion implanter, and this basically forms your N plus region in the substrate. This is followed by the contacts at the bottom substrate. The next step, please note down, these are fabrication steps, and it's very important and very critical. So once you have the source and drain and your substrate contacts, you create a contact window and deposit and pattern the metal layers. Metal layers. So since it is a 4-terminal device, the remaining 3 areas where you need to develop the contacts windows, deposit and pattern the metal layers would be the source, the drain, and the gate. The body has already have those substrate contact prior to this. So you please note down the simplified process sequence for the MOSFET, for the fabrication of the MOSFET. Metal oxide semiconductor field effect transistor. Hello?
Yes, sir.
Okay. Can we go to the next slide?
Yes, sir.
Any questions on this? So I think this will further explain what we just talked. So you have a silicon based substrate which is intrinsic in nature. Then what you do is you have an oxide layer. Basically, there are two types of oxide. One is at the edges, which is basically for isolating one transistor to another, and the other is the oxide which is just above your substrate and just below your gate, which is basically acting as an insulator. Okay, so the oxide at the sides, on the sides, would be for isolating one type of transistor with another so that they don't get shorted. Okay, so different types of oxides are formed. So first, to make this gate oxide, you deposit a thin layer and then do the patterning. Patterning is basically like you deposit it all over your substrate and then you put a type, either a positive or a negative photoresist, and then you expose to the ultraviolet light. So this is basically which so here you can see the ultraviolet light you are exposing, but it is having a mass such that some part of the exposed photoresist is becoming soluble and it reaches up to your oxide, gate oxide, while the other is there is an obstruction. So this is basically your mass, glass mass. So this is very important step through which you form different patterns or the patterns that are desired by you. So you expose through this ultraviolet light. So you have two things. Because of this ultraviolet light, to the exposed region, the photoresist becomes soluble, and due to this mask, this region which is not exposed to the ultraviolet light is the insoluble part. Hello, are you there?
Yes, sir.
Just a moment, there's something went wrong. Yeah. So this part is the insoluble photoresist, while the exposed part, exposed to the ultraviolet light, is the soluble part of your photoresist. Remember, photoresists are two different types, positive and negative. We shall not go into detail. After this, there is the other step, which is the etching. By English term, it will just removing by using a combination of hydrofluoric acid or by using a plasma technique. So that is basically called the dry etching. So you are either having a chemical etching or the dry etching of the photoresist which is exposed. And once you have this hardened photoresist and you expose to the chemical etch or your dry etch, it will lead to the etching of the oxide region here in this area. And these are this is the remaining area where you are having silicon dioxide. So here a full step has been performed to achieve silicon dioxide on silicon substrate at the desired region, generally called the active region. So this is basically how, so these steps are kind of repeated all the time to form patterns, to expose the region and to etch away the undesired oxide or metal depending upon the requirement. So silicon substrate, as we have mentioned, it is not a 2D thing. It is either coming in a disk, but this is also a simplified version. So when you cut into a die, it in a rectangular or a square manner, you would see the three-dimensional silicon substrate with an oxide layer on the top like this. Using the photolithographic patterning sequence, what one can achieve is that we have mentioned before. What we see is the silicon dioxide as shown here. So the one which we had seen previously, it was a two-dimensional representation of this three-dimensional structure. So here you can see this is your silicon substrate, and here on the top of this, on the sides, you are having silicon dioxide. So let's move further. Once we have achieved this up to here, there are many small steps in between to achieve silicon dioxide that we have mentioned before. The next step would be having a thin oxide, which would be forming basically your gate oxide. So this oxide is for isolating the transistor on either side, either this side or this side. So this is basically at a later stage what you will call as the thicker field oxide. So it is isolating one transistor to the next one. So these are all two-dimensional representation of a three-dimensional structure. Again, you deposit this by some plasma technique, a very thin oxide structure like this, and on the top of that you deposit the polysilicon, which is having the properties of metal on the top of your thin oxide, and then you perform the same sequence of step to get a particular pattern. You expose them to the UV. You first have a photoresist on the top of it. You expose using a particular mask to the ultraviolet light, and you get the desired structure like this of polysilicon. This then again you follow the same sequence of step to get the desired silicon dioxide structure, where the patterning happens because of the sequence of operation happening in the cyclic manner. What are the sequence of operation to get a pattern? It is depositing polysilicon, then getting a mask, exposing the ultraviolet, exposing the desired part with the ultraviolet, and then etching away the other part. So deposit, exposing, and etching. Deposit, exposing, and etching. So this is how you get the desired structure. You have polysilicon, and you have a thin oxide, and you have thicker oxide at the edges. Once you achieve this, then what you need to do? You need to get these source and drain. Remember, this substrate would be, this silicon substrate would be a p-type substrate, because since this is n plus and n plus, this would form your source and drain. So here you do ion implantation. So this structure is already there. Now you need to do ion implantation. This area would not get affected. This area would not get affected. Here you already having polysilicon. So polysilicon has very high density of electrons. So N plus. So if you are doing ion implantation, only this area and this area will show reflections of change. It will change to N plus and N plus region, which is forming your source and drain. So now you are having source, drain, gate. Polysilicon is gate, and oxide, which is this thing. So this becomes a structure which is what we desire, almost making a NMOSFET transistor. So after this, so you just consider up to this region. This is almost making of a single NMOSFET transistor. But you also need to have a metal at the bottom and at all the three regions. So you have these thicker oxide for isolation from different transistor here and here. Then you have this metal oxide semiconductor, okay, and then you have source and drain. So now you need to do metallization in all these four terminals. Okay, you need the wiring, metallization or wiring through these contacts. So you need a contact formation at the source, the drain, the gate, and the substrate. So again, you deposit another layer, other insulating layer over the thicker silicon dioxide to make the structure more robust, and you further isolate the gate and polysilicon gate and silicon dioxide insulator with the rest of the active region. So this from here to here is your active region. These are acting as a isolation to the next transistor on either sides. So if you think as a 2D, so if you see it in the Y direction or in the X direction, there will be transistors all over on the left hand side, right hand side. So minus X plus X, minus Y plus Y. If you see this as a two-dimensional, the transistor in a two-dimensional manner, it will have in the minus X and plus X and minus Y and X plus Y. So you need to have isolations. This field oxide is acting as an isolation. So as I mentioned before, you need to do a metallization of your source and drain. So this is the next step that is followed. So metallization is deposition of the metal, here being aluminum, so that your source and drain is connected to the external world, from where you can apply to any kind of a oscilloscope or any kind of a multimeter, okay, or any kind of voltage source or current source. So again, you do all kind of steps to get the pattern, and you are having here is a source with metallization and the drain with metallization. I think it has missed a couple of steps. One step is the metallization at the bottom substrate, along with the metallization of to the gate. so that you can give voltages not only to the gate but also at the substrate. So you will have metallization on source, metallization on drain, gate and potting. So basically this is a N MOSFET transistor, and this silicon is P type, P type, P type. So this is the process flow for fabrication of N type MOSFET on a P substrate silicon. Hello? Hello?
Yes, sir.
Yes, sir.
So this is a one-dimensional to two-dimensional representation of a three-dimensional process. Okay. So if you understand, you should be knowing all these basic steps. Now, like in the company, you would be doing some layouts. So to make these, you make the layouts. So this is how you would actually make the various masks, and this is how you would visualize your MOSFET transistor. Okay, so this actually, if you view from the top, you have input, you have output, you have for the P MOSFET, you have you would have P MOSFET, you would have N MOSFET, and the drain of your P MOSFET is connected to your VDD or the voltage source or the battery, while the source of your N MOSFET is not only connected to the output but also connected to the drain of the N MOSFET. So one which is reflected on the left hand side and one which is reflected on the right hand side. You should understand. So this actually is giving you the layout diagram for a CMOS configuration where you are having a PMOS and a NMOS. This NMOS drain and PMOS drain are connected to each other as well as the output. While if you see here, this one, so this is the gate of your PMOS and NMOS connected to the input. And then the source of your NMOS is connected to your ground. So this is, if you basically try to look from the top. So when you are fabricating a CMOS, till now we have just talked about a simple NMOS transistor. But what is CMOS? CMOS is having both PMOS and NMOS transistor. So again repeating, what is CMOS? CMOS is complementary metal oxide semiconductor, and it has both NMOS and your PMOS. So you're having two different types of transistors. So again, you will have a thicker silicon dioxide or the field oxide between these two transistors. So this is a three-dimensional representation of your CMOS fabrication steps. I think it will talk about the CMOS fabrication steps. So instead, here you start with a P substrate, and then you are already using the patterns. You grow the field oxide between the two transistors, which is here and here, as well as the adjacent transistor, which is here and here. So these are all field oxide, which is acting as a isolation layer between different adjacent types of transistors. So here we will be talking about PMOS and NMOS. To get that, if you are having a P type of substrate, you would require, if this is a P type of substrate, you would require a formation of N well here. So this region would ultimately lead to your N MOSFET transistor, while this region in which you are having N well would lead to formation of your P MOSFET transistor, which are isolated by the silicon dioxide layer, a thick silicon dioxide layer. In both the cases, you would have the gate oxide. So let's go to the procedure here. Yeah. So what you are actually seeing is this thing. You are having a polysilicon acting as a gate here. On the top of this thin oxide. So this region would be forming your P MOSFET, and this is the input. This terminal is your input. Yeah, somewhat like this. Please note down this. This will make you understand everything. Please note down this. So here, what you are having is formation of your N MOSFET transistor. And here, what you are having is the formation of your P MOSFET. And this is the layout. Okay, so this is where you're seeing N well. So N well would be having P plus source and drain, and P plus channel, while your N MOSFET. So this is basically the layout of a simple inverter. In other words, of a CMOS, of the complementary MOS. So complementary means NMOS and its complement is PMOS. That is, they are almost opposite to each other or bang opposite to each other. Complement, they complement each other. Class, you there? Please note down this much. So
Yes,
that,
sir.
yeah, I think it's very important. So here you can see you are having VDD, which is the voltage source that you are giving, and this is the contact, and this is the in between you have a formation of your source here. So it goes to the source here. Then in between your source, this is your drain. So this is your gate. This is where you are having gate. So gate of one is connected to the gate of the other. So gate of your PMOS is connected to the gate of the NMOS system, and you are also having the input from where you give the desired supply. It can be 1, it can be 0. So drain of your PMOS is not only connected to your NMOS, but it is also giving the output here. So as we mentioned, to have a PMOS, you would require an N well and have a complementary number of steps as in the formation of your NMOS transistor. And here in your NMOS, the ground is connected to the source is connected to your ground. Well, here the source is connected to your VDD in your PMOS. And the drain of NMOS and PMOS are connected to each other as well as the output. So this is the layout. So you form patterns like that so that you get a simple inverter. Similarly, if you are able to make a inverter, that is a gate. Inverter is a NOT gate. So if you are able to make an inverter, similarly you can make the other two universal gates. What are those? NAND gate and NOR gate. Again, using NMOS and PMOS in parallel and series. Hello? Are you still on?
Yes, sir.
So this is your polysilicon gate. Please note down this. Once you are able to understand this, then you can make any extended form. And then there shall be a lab session later on to first make transistors, then make simple inverter, as in the layouts and everything. This being a very introductory class. If we are able to do say a simple NOT gate or simple NAND gate or 2-input NAND gate or 3-input NAND gate, it would be good enough. Making through transistors. That is how it is happening in the industry. Instead of one, you are now talking about like in the 70s they make it with say 1,000 or 10,000, something like that, few thousands. Now you're talking about billions of transistors, billions of gates. So remember, whenever we are talking about gates, we just need to either divide it by 2 or 4. Why? Because all the circuits are made up of universal gates. What are the universal gates? NOT gate, NAND gate, and NOR gate. So NOT gate is made up of 2 transistors. NAND gate is made up of 4 transistors. NOR gate is made up of 4 transistors. So all you need to do is to get number of gates, you just need to divide it by 2 or 4. So you will get a rough idea. So once we are talking about billions of transistors, just 1/2 or 1/4 of it are the number of gates that are there inside your chip. Hello? You still
Yes,
there?
sir.
Do you have a class now? I don't hear you anything.
Yes, sir.
So I think let's meet tomorrow.
Yes, sir.
Right. So I will discuss with Mansa or Sanya or Manas or Ishan or any one of you just who would like to volunteer and let me know so that we are also able to do the different type of scalings. I will also give you some overview about some of the design rules that I use for these fabrication steps for making the layouts, as well as how do you scale down the transistor. So there are two major ways that we have already talked about: constant field and constant voltage. And there's another approach which takes advantage of both these systems, both these approaches, namely constant field and constant voltage scaling. And what you get is a generalized scale. And there shall be some numericals based on that in your exam too. So that's a hint. So yeah, let's fix it for tomorrow, or or maybe Wednesday. Let me have a word with Mansa and please be there. Thank you. Any questions?
So which
Hello?
simulation software will we using?
Synopsys is the simulation software which is available, I think, in your lab. We are also requesting for Cadence. So these are, as we mentioned, these are electronic design automation tools. So right in the beginning, we were just talking about device. It doesn't have all these so many licenses, so you can use it at different time, having some remote access, or you at least getting exposed. Those who want to do some projects, that would they would be, it would be helpful for them because it would be demonstrated to you. But since there are so not so many licenses, like in the IIT Mumbai or Delhi, they are having 30 licenses, 50 licenses, even in triple ITs and NITs. So I think as time progresses, we shall have more number of licenses too. So in digital, in the VLSI design, you have uh, electronic design automation tools like Cadence and Synopsys, which is used all over the world, right from Xilinx to right from I guess Intel to Nvidia and Apple and so on and so forth. I think I'm not very sure of which particular tool is used by whom, but that industry people would be able to tell you better. But there are so many of them, and then there are the Indian partners who are doing these. So in India, VLSI design is already existing in a very big way. You can just go Google search for VLSI design. They want very good engineers who have got good this thing on layouts. Even in fact, my previous PhD student, she had worked for in JNU, had worked for 4 years in a semiconductor VLSI based company, very well known LSI. So similarly, you have Apple, you have Intel, you have Nvidia, you have Qualcomm, you have Samsung, Broadcom. It goes on and on. And then you have so many of the local vendors too. Everywhere you need to design to make chips. It's a huge ecosystem. It's a huge ecosystem. And they need a lot of people in India. Forget outside India, there's a lot of opportunity. They want all good people. So if you have those skill sets, is what they're looking. First, basic knowledge, and then hands-on. Basic knowledge is a prerequisite. Otherwise, they will say, "Oh, this guy is not good enough." They go and recruit in all the IITs and everywhere. First thing they look is your basics. If I say, oh, what, how do you basic definition of MOSFET, it's or layout or HDL or transistor or Those are required. So in the industry, cadence and synopsis are used in a very big way. So that is like, when they say that there is a gap between academia and industry, it is because people are not exposed to such kind of tool which is used in the industry. But these tools are available. IITs being a privilege, all these people, institutes are having lot many number of tools. We also are requesting, if good number of licenses are brought, then you would be exposed and you can design stuff like that. You can design all these digital design, and then so fabrication comes later. Like if you're making a house, the architecture first designs and then gives the architecture, then you go for the next step, which is fabrication of your house. So first transistor, then kind of making different blocks, so on and so forth. Any questions? It's already 3:15. Are you free, Manas?
No, sir. Sir, we have.
Okay, then let me go. Otherwise, you shall be late for your
Yes.
next.
Yes, sir.